Alright, we're continuing in the section on autonomous differential equations. And so I thought maybe we would look at a specific example just to see um, if we got what's happening in these equations. So suppose I've got something that's going to be pretty hard to solve. Pretty hard to solve. That is, consider dy over dt equals the sine of y. Okay, and so what we want to do with all autonomous differential equations initially is to always find the equilibrium. So equilibrium solutions. We said that we set the function equal to 0 and solve. So in this case we just have sine of y equals 0. Okay, we all remember where the sine function is equal to 0. That's where y is equal to 0, plus or minus pi, plus or minus 2 pi, multiples of pi, etc. Oops. Good. 2. Why don't we go ahead and take a look at the plot in the y prime plane. And so if we draw the y prime plane, we just have the sine function. We'll draw 1 back. Okay, so that's minus pi, minus pi, pi, 2 pi, and then of course it would repeat. Okay, let's transfer that information over to the ty plane. And so our equilibrium solutions, I'll go ahead and put the equilibria in red. It's going to be at minus pi. Okay, these arrows are representing the direction of travel, right? Let me get that better. Okay, so that's it. Minus pi. And then there's one at 0. Oops. Okay, and then there's one at pi. And then there's one at 2 pi. Of course, it repeats itself over and over again. Okay, now what's happening? Between 0 and pi, y is increasing, and then y is decreasing, and then y is decreasing over here. Okay, so then on the other side of minus pi, by the way, we're increasing, right? So over here, y is increasing, then y is decreasing, then y is increasing, and y is decreasing, then y is increasing. Okay, and so if we just kind of sketch in what's happening, for example, between 0 and pi, the solution curves are going to be looking something like that. And then if we start between pi and 2 pi, our solutions are going to be dropping down. And then above, we're going to be going up. Let's see, over here we'll be dropping down. And then here we'll be increasing. Okay, so from our graph or from the direction field, let's classify the equilibria. Okay, so at this equilibrium at negative pi, do we have a positive crossing or a negative crossing? And if we have like a negative slope crossing, negative linear crossing, that means that we're going to have a situation like this in the direction field, and that means our equilibrium is attracting, or I guess I didn't use that word before. It's either stable or a sink, and so y equals minus pi. Maybe I'll do it this way. I'll say stable will be y equals minus pi. That's asymptotically stable. It's converging. And then looks like y equals pi is another one. And so what would the next one be? I think it would be y equals 3 pi, and so on. Okay. And then for the sources, or unstable. We have y equals 0, y equals 2 pi, y equals 4 pi would be the next one, etc. Very good. And so just as a quick example here, another example might be of a question might be if y of 5 equals 6, state the limit as t goes to infinity of y of t. Okay, so to tell you the truth, it doesn't really matter what time we put in here, right? Because we said that our local slopes only depend on y. So here, where is y equal to 6? Yeah, I think it's going to be just below 2 pi, right? So in other words, at time, if this was like time 5, then my initial point, oops, I'm trying to get a different color here, is just below here. Okay, and so where is that solution going to go as t goes to infinity? Well, it's all these solutions are going to be heading towards pi. Now, so that means that the y of t is heading towards pi. Now, I said that it didn't matter what the initial time was. Is that true? So suppose you start here, or start here, or start here, or start here, or start here, right? You're always going to be converging to pi. So it really doesn't depend on the initial time in that case, right? The overall behavior is always going to be the same. Very good. Okay, so now that we've got a more elaborate example under our belts, let's talk about some properties and some theory for autonomous differential equations. Okay, so key property. Oops. Key property of autonomous DEs. So functions or solutions to an autonomous DE are either 1. Always increasing, 2. Always decreasing, or 3. Constant. That's it. Why is that true? Suppose that this is the ty plane and I have a function, and suppose that my function is increasing there. Is there ever a time out here somewhere where the function can decrease again? Can this ever happen? And I think you'll see that the answer is no, because at this particular value of y, right, if you have this slope of the line here, then if you come over at any point in time later, it's also got to have that slope, right? So therefore you can never come back down. If you increase through any value of y and your system is an autonomous, or your differential equation is autonomous, your solution can never come back down. Therefore, that's why solutions to an autonomous differential equation are either always increasing, always decreasing, or constant. Okay, so that's kind of an important thing to realize. In fact, you could come up here and see, notice that all of our solutions, right, in the direction field are always increasing, always decreasing, or constant. Okay, good. So that's a key property to remember. And now, theory about stability. Stability. I think we've already talked about this, but if you have a crossing that looks like this at point A, right, this says that f of A is equal to 0 and f prime of A is negative, right? This is y f of y, or y prime. Then this says that you have a stable equilibrium. Okay, similarly, if you have a positive one like that, if f of a is equal to 0, that makes it at equilibrium, and f prime of a is positive, right, then you have an unstable equilibrium. Okay, and then if f prime of a equals 0, we have no conclusion. You'll remember that in one of our videos that we couldn't say anything about that. Okay, one last property that I wanted to talk about, but it's getting a little bit late in this video, so I think I'll wait and tell you about concavity in our final video. Okay, see you then.